All right, so this is what we have left. Today we're going to talk about the comparison test. Okay, so far we've seen how to determine the convergence of a geometric series. A P series, and some other ones, and a few other series. That's what we did so far. Now, what we're going to do with the comparison test, we can test the convergence of any other series, practically any other series, by comparing their terms to those of a series we know converges. So that's what we're going to do in this section. So theorem 10, the direct comparison test. For convergence. Let sigma, the summation of A sub n and the summation of B sub n be two series with both positive and where A sub n is less than B sub n. For all n. So these are series that are finite or infinite. So they're going to be infinite or finite series. N goes from 1 to k, and goes from 1 to k. Then, if the series, the B sub n series converges, then the A sub n converges because of that. They're positive series, so they're greater than 0. And if B sub n converges, it means it's finite. It's got a value. Then A of n is bounded, so therefore it also converges. Well, I think we already did this one. I'm sorry, because this sounds familiar with what we talked about last time. So because of this, if B sub n, the series B sub n converges, that means A has to converge. Likewise, if A sub n diverges, then the series B sub n also diverges. In other words, if it goes from 0, this goes to infinity, that means B sub n, since it's greater than, has also got to be go to infinity. All right, let's look at some examples here. Here's the first example. Example 1. A. The series n equals 1 to infinity, 5, 5, n minus 1. Does it converge or diverge? So, 5/4. N goes to infinity, so this thing goes to by each term by 5. Since it's only one n in there, so we get 5 divided by 5, 5n divided by 5, 1 over 5, n equals 1 to infinity. This becomes summation of 1 over n minus 1 over 5. As n goes to infinity, we know that the series is larger than 1 over n, because if that's 10, this is 10 minus 1 over 5, so this is going to be smaller. Is greater than the nth term. So in other words, instead of a sub n being less than b sub n, it's a sub n is greater than b sub n. So it diverges by theorem 10. B. Let's examine the series n equals 0 to infinity, 1 over n factorial. No, a factorial is the product of everything from n minus 1, n minus 2, all the way down to 1. So 3 factorial is 3 times 2 times 1, which is 6. It's a product. So what this gives us, 1 over 0 factorial plus 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and so on and so forth. So 1 over 0 factorial is 1. 1 factorial is 1. That's 2 times 1. That's 3 times 2. This is 1/6. 1/12, and so on and so forth. All right, so we can compare it. we can compare this sequence set 0. If it's going to be bigger, so that's going to be less than. So each of these values, so in 0, it's 1, 1 over 2, this is bigger than that. So we have to have so, and we know 1 over 2 diverges or converges. As we see what we have here, so this is 1 plus a half, plus a half squared, plus a half cubed. So this becomes 1 over divided by 2n plus a half. It's 1 plus 2. So it converges. Since this one converges, this one has to converge. Because we're comparing it to this sequence, 1 plus summation of 1 over 2 power n. Right? There's another way to compare it. That's by individual terms. Now we have the limit comparison test. For series where the series is rational. This brings us to theorem 11. The limit comparison test. Suppose A sub, we have positive sequences. For all n greater than or equal to some integer. So we have positive sequences. Then, if the limit as n goes to infinity of a sub n over b sub n equals some value c, some constant value, where c is some value greater than 0, because a and b are 0, and the ratio is going to be positive as well. Then the summation of a sub n, summation of a sub n, and the summation of b sub n both either converge or diverge. 2. If the limit as n goes to infinity of a sub n over b sub n is equal to 0, and the denominator converges, then since this becomes a finite number, then summation of a sub n also converges. So if the limit as n goes to infinity of a sub n over b sub n equals infinity, if a sub n equals and summation of b sub n diverges, then summation of a sub n also diverges. Right? So example 2. Which converge, which diverge. So we have A, 3 over 4 plus 5 over 9 plus 7 over 16 plus 9 over 25. This is equal to the summation of n equals 1 to infinity 2n plus 1 over n plus 1 squared. All right, so which one converges, which diverges? So we'll be looking at theorem 11, see what happens here. So we have the summation of n equals 1 to infinity 2n plus 1 n plus 1 squared. Just in case. We FOIL off the bottom. So that's a sub n, and this is b sub n. So as n goes to infinity, we have 2n over n squared. which is 2 over n. Because yeah, I mean, as n goes to infinity, dictates the top, this dictates the bottom, so we get that. So we look at this comparison. This is a constant multiple, doesn't matter. And 1 over n according to these theorems. So, okay, which one? So, 1 over n. We look at the limit. This diverges because it starts off at 1, then it goes to 1/2, then 1/3, and so it diverges. There's no end to it. So the limit as n goes to infinity of a sub n over b sub n so as n goes to infinity, that goes to infinity, that goes to infinity faster. So we get that's what we had up here. This becomes the limit is 2. As n goes to infinity, this becomes 0. This becomes nothing. So it's infinitely small, so we like to put 2. So the top diverges, the bottom diverges, a sub n diverges, B sub n also diverges. So the sequence itself diverges. If I divide everybody by 2, I divide everybody by n, sorry. So we got our n squared. So we have 2n over n squared, 1 over n squared. So it's 2 over n, 1 over n squared, 1 plus 2 over n. So this goes to 0, that goes to 0. That goes, so it's 0 over 1. And it goes to 0. So the comparison tests. Yeah, not first that here. So the bottom dictates so it has 1. So I have 2 over n. Okay, that's what I said. So since this limit, in our case, the limit, we just did the limit, we get 0. So 0 over 1 is 0. That's the limit. And it's not, C is not greater than. So therefore, since the top diverges, it goes to infinity. Since the top diverges, and that means the bottom diverges. So yeah. So looking at both of these, since our limit equals 0, but our bottom doesn't converge, the summation n squared plus 2n plus 1 diverges. So since it diverges, a sub n diverges. So the whole function diverges. Yes, that's what it is. So the second one, let a sub n equal 1 plus n ln n over n squared plus 5. So as n goes to infinity, n ln n squared plus 5. So this eventually goes to ln n over n squared, ln n over n. So this is bigger than 1 over n. We know the summation of 1 over n diverges. And since that diverges, this diverges. So it diverges. We know we have one comparison, 1 over n. So this one is the same thing as ln over n. And like we did last time, we had 2 times 1 over n. Since 1 over n diverges, then 2 times a divergent equals a divergent. All right, let's look at number 3 now. It's asking example 3. Does the summation as n equals 1 to infinity ln n to the power 3 halves, does it converge? So what happens here? We have our ln n over n to the 3 halves. We have to have a sub n less than b sub n. So we have to compare it to ln goes like this. So we do n to the power 1/4 or 1/3 even. But no, 1/3 gives a positive and negative. So we do 1/4. Yeah. Since this is less than this, ln n we have to find a value because the denominators are the same. We have to compare the numerators. So ln n is less than n to the power 1/4. Ln n goes like this. So the smaller the numerator, the bigger the function is going to be. So let's look at that. So we have n 1/4 minus 3 halves, 6/4, and negative 5/4. So it's 1 over n 5/4. So let ln n over n 3 halves equal a sub n, and 1 over n 5/4 equal b sub n. And we get the limit as n goes to infinity of a sub n over b sub n equals ln n equals the limit of that becomes the limit as n goes to there. Take the top, leave it alone, times the flip of the bottom. So this becomes 6/4. So we have the limit of ln 6/4 is ln or n to the 1/4. As n goes to infinity, that goes to infinity, that goes to infinity. You get the limit as n approaches infinity. The derivative of ln is 1 over n. 1/4 n to the power -3/4. Limit as n goes to infinity of 1 over n. Times 4 over n/3/4. Negative them there. So this is 4/4. So we get the limit as n goes to infinity of 4. 4/4 mass is 1/4. Now as n goes to, so we have as n goes to 0 or infinity, that one goes to 0. So our function converges. All right. That does it for that section. Oops. All right. That's a comparison test. So basically all we have to do there is find so to find the comparison test, we first have to have that has to be true. And then check the theorems. Okay, theorem 11 says that if the limit as n goes to infinity of a sub n over b sub n, where this is true, if it equals some constant, and that constant is strictly greater than 0, then the sequences converge or diverge. If the limit as n goes to infinity of a sub n over b sub n equals 0, and the summation of the denominator converges, then a sub n converges. If the limit as n goes to infinity of a sub n over b sub n equals infinity, and summation of b sub n diverges, then a sub n diverges. So now let's look at the ones that don't exist. Let's say limit of your ratio equals c, and c is equal to 0. Then we can't do this. It has to be c is greater than 0. The ratio, if it equals 0, the limit as n goes to infinity, and check the bottom. Does it converge? Does the summation of all those denominators converge? If it does, then a converges. If b diverges, then a diverges. If your limit as n goes to infinity of the ratio goes to infinity and the denominator diverges, then the top diverges. If it goes to infinity and, well, it can't converge because it goes to infinity. All right, so that does it for that section.